Hi there, this is Professor Shannon Gracey, and today we'll be covering optimization examples from the Larson and Edwards Calculus text. So our goal today is basically to solve applied minimum and maximum problems. So we're going to be using the skills that we learned in curve sketching or for curve sketching, like the first derivative test, the second derivative test, and critical numbers. And we will be figuring out where, the maximum and minimum of an applied function falls. So here we go. Basically, what you need to remember is this is just like in pre-calc when you were given, something along the lines of, Farmer John has an area that he wants to fence in, and he has, this much fencing. So basically what you had to do is you had to figure out how to write a function in a single variable, and then you used your calculator and all that good stuff to figure out what the maximum area would be or something like that. So you still need to use or utilize those skills. But now what we will be doing is using our calculus methods instead of our calculators to find the maximum and minimum, or maximum or minimum. Here we go. Step 1, analyze. Make a sketch if possible. Picture is worth 1,000 words. Write down what you know, what you need to find, and oftentimes what will happen is that will loosen something up in your brain, and you'll remember something else and something else and something else, and before you know it, the problem will be finished. Now, you write a primary equation for the quantity that you're optimizing, which is a generic term for maximizing or minimizing. If you look for the word, find the maximum something, find the minimum something, it is that function or relationship that is to be optimized. Oftentimes, or you will usually be given supplementary information. Sometimes people call it a secondary equation, that where you can utilize that information to reduce your primary equation into a single variable. So that would be your third step. And then fourth step, you don't have to spend a huge amount of time on this, but it's good to determine what the feasible domain of your primary equation is. If you have area, you would not have, a negative amount of feet or something. Or if you're dealing with time's never negative, that kind of stuff. Then optimize by finding the zeros of the critical numbers. And part of the optimization is to verify. So you need to use the first or second derivative test to ensure that you have indeed found a maximum or minimum. And then find all the values by back substitution, and then write your conclusion in words. Does it make sense? We need to always think about that synthesize step. We need to make sure our conclusion makes sense. If you find that the maximum speed of the bicycle rider was 5,000 miles per hour, you might be off a little bit. All right, here we go. Let's start off relatively easily by finding two positive numbers that satisfy these requirements. The sum of the first number squared and the second is 27, and the product is a maximum. The analysis of this one is going to be naming the numbers, really. So here, if we let x be the first number, and we can let y be the second number, Now, let's take a look here. Before we dive too deeply into this problem, let's figure out what our primary equation is. We can always go back to the analysis step if we need to. What words are near the word maximum? Well, maximum is here, so let's backtrack. Oh, the product is a maximum. So that bugger was a little sneaky, right? We did not have any numbers there. So let's see what we have for our primary equation. Our primary equation would be P for product in terms of X and Y is equal to X times Y. The product is a maximum. That helped with our primary equation. Now, in order to reduce to one variable, let's check out what we had. So some secondary information would be the sum of the first number squared, and the second is 27. So let's write that in. The sum, so there's a plus sign, of the first number squared and the second is 27. Cool so far? Good, good. So this was that secondary information. Now notice in this information, it's an equation where we can isolate one of the variables. Which variable is easiest to isolate? Well, the y is, because it's not squared. Okay. Now, taking our product equation, remember that our product in terms of x and y was equal to x times y. But we have now written y in terms of x. So the product in terms of x alone is going to be x times, good, 27 minus x squared. All I did is I isolated the y and wrote it in terms of x. Good so far? So now, simplifying that a little bit to make it easy to differentiate, we'll get 27x minus x cubed, and that is our primary equation reduced to a single variable. Are we good so far? Awesome. Now we optimize and verify. So the optimize step, remember, was to find the critical number or numbers. Oh, actually, don't forget, we need to talk about our feasible domain. So over here at our primary equation, the feasible domain is that both x and y need to be positive. So they both need to be greater than 0. Now we know that y is equal to 27 minus x squared. So that has to be greater than 0, which means that 27 would have to be greater than x squared, meaning that we would have to have what? Think about 27 minus x squared. That's that would be a parabola opening downward. So it's basically gonna be up here at 0.27, and then you'll have it somewhere here, which is root 27, which of course is 3 root 3, would have to be greater than x. But remember, you're going to get a plus or minus, right? But we don't have to consider that minus because x has to be positive. So now, if we do our picture, it would look something like this for the domain. So what that means to us is that the feasible domain is going to be from where to where. We want positive outputs for the y, and that occurs from, that occurs from here to here. Cool so far? So, y or x rather, needs to be greater than 0, and x needs to be less than 3 root 3. 3 root 3 is, get the calculator going. Is approximately 5.2. All right, so here we go. Finding the critical numbers. So our primary equation was P of x is equal to 27x minus, I believe we had x cubed, yes. So differentiating both sides with respect to x, we will have P prime at x is equal to 27 minus 3x squared. Good so far? And then how did we find the critical numbers? Beautiful. We set the derivative function equal to 0 and solve. So we'll get 3x squared is equal to 27. Dividing by 3, we'll get x squared is 9. And square rooting, we'll get x is plus or minus 3. Now, our critical number is going to be what? See how much room I have. Our critical number is going to be positive 3, because 0 is less than 3, which is less than 3 root 3. So that's our critical number. So now we need to verify that this yields a maximum. So this was the optimize step. And then the verify step means that you would either use the first or second derivative test, to ensure C equal to 3 yields a maximum. All right, well, since we have a really easy first derivative function, I will apply the second derivative test. So differentiating both sides with respect to x, we will have p double prime at x is equal to negative 6x. And if you recall, to run the second derivative test, you evaluate the second derivative at the critical number you found by setting the first derivative equal to 0. And so we will have a negative value, and a negative value means that at your critical number from the first derivative, your function is curving downward. So that implies a relative maximum. And so this one, I'm using the second derivative test. Cool? All right. Now, what we also need to do on this guy is we need to find the other values. So let me see what step I put that in. So let's write this in here. Our job was to find x and y. So now what do we need to do? We need to find y when x is 3. So to do that, we will have y was equal to 27 minus x squared. So plugging in x is 3, we'd get 27 minus 3 squared, and this will yield, good, 18. Writing our conclusion in words, we can say the first number is 3, and the second number is 18, and we're all done. So all of this work will be looked at if you're in my class and you're taking an exam, but the actual conclusion is here. All right? Now, at any time, please feel free to pause the movie and try the problem yourself and see how you do. But right now, we'll go ahead and take a look at number 2. A woman has 2 dogs that do not get along. She has a theory that if they are housed in kennels right next to each other, they'll get used to each other. She has 200 feet of fencing with which to enclose 2 adjacent rectangular kennels. What dimension should be used so that the enclosed area will be a maximum? Alrighty, well, let's see what we have going on. We've got this kennel. And so that she doesn't waste her fencing, she put a segment of fencing down the middle there. So if we let W be the width and L be the length, we'd have something like this. So L would go all the way across like that, and then W would be here. Now, what is our primary equation? Good. You go to the word maximum, and we want to maximize the enclosed area. Writing down, why don't we call it A for area? And area in terms of length and width is equal to, beautiful, length times width. It's a rectangle. Good so far? Now, the feasible domain. What do we have going on? Actually, let's reduce this to one variable first. Over here, what do we know? We know that we have 200 feet of fencing with which to enclose these adjacent rectangular kennels. So that means that what? Good. How many W's do we have? We have 3 W's. How many L's? Beautiful. 2 L's. And that's got to equal to 200. So you decide which one you prefer to isolate. I'll go ahead and isolate L. So we get 2L is 200 minus 3W. And then we'll get L is 100 minus 3 halves W when we divide everything by 2. And remember our area. So now I'll go over here. Our area in terms of L and W was L times W. Our area in terms of W alone will be 100 minus 3 halves W times W. And we can write that as 100 W minus 3 halves times W squared. So our area in terms of W is 100 W minus 3 halves W squared. So now, coming back to our feasible domain, again, we want both the length and the width greater than 0. Otherwise, we will have no kennel at all. Utilizing the fact that L has to be greater than 0. Actually, let's get this in terms of W. So 100 minus 3 halves W has to be greater than 0 because that's our expression for L. So 100 has to be greater than 3 halves times W. So 200 thirds has to be greater than W. So putting that together with W having to be greater than 0, but less than 200 thirds, we have our feasible domain. All right, cool. So now let's go do our thing. Optimize and verify. So the optimize part, we're going to find critical number or numbers. And to do that, we use our area function. And we, good, differentiate with respect to W. which will give us a prime at W equals 100 minus 3/2 times 2W. So a prime at W is 100 minus 3W. Good so far? Awesome. So finding the zeros of this, we'll get 0 is 100 minus 3W. 3W is 100. So W is 100/3. And we can now say that C is 100/3 because C falls within 0 and 200/3. So over here, going to the verification, I'm going to use the second derivative test because the function is very easy to differentiate again. So starting with a prime at W is equal to 100 minus 3W. Differentiating both sides with respect to W, we will get a double prime at W is equal to -3. And then plugging in our critical number from finding the zeros of the first derivative, a double prime at 100/3 is still going to be good. -3, which is less than 0, which implies a relative max. Beautiful. So now, what do we need to find? We need to find, great, we need to find L. So, recall that L was equal to, forgot already, L was equal to 100 minus 3/2 W. And plugging in W is 3. We will get that our length is 100 minus, oh no, my bad, we're not doing W is 3, we're doing W is 100/3. So this is going to yield a result of 50, and so our length would be 50. So putting that all together, the dimensions of the kennel which yield the maximum area are 50 by 100/3, and I think that was in feet, wasn't it? Let's see what we have. Yes. Alrighty? Very good. Now we're looking at another rectangle, but it's bounded by the x-axis and the semicircle y is 25 minus x squared. What length and width should the rectangle have so that its area is a maximum? Well, let's check it out. We have we make this plus or minus 5, and this is x and this is y. And recall that y is equal to the square root of 25 minus x squared. So we get this semicircle right here. And so here's our semicircle, and then we've got a rectangle that's bound inside of here. So what we want to find is what? Again, good. We want to find maximum area. And the maximum area we're interested in is the maximum area of the rectangle. So our primary equation, area in terms of x and y, is equal to, now we have to figure out what this rectangle would look like. So if we just say, I don't know, at any given time, we've got something over here, and let's say that this is negative x, and over here we have a positive x. I don't know where that is going to be, but the rectangle would look, whoops, I didn't do that very symmetrically, did I? The rectangle would look like this. And our job is to figure out where this happens. So these ordered pairs here would be x comma y, but y is root 25 minus x squared. Over here we would have negative x comma root 25 minus x squared. So this base right here, our base, do you see, of our rectangle would be x minus negative x, which is 2 x's. Good. So the base is 2x, and then times y. Now, reducing to one variable, the area in terms of x alone is going to be 2 times x times the root of 25 minus x squared, because that is our y. Okay, so far? Perfect. All right. I'll just kind of point that out here. This right here is y, which is root 25 minus x squared. Groovy. So now here we go. Let's do our thing. We're going to optimize and verify. So area in terms of x alone is equal to 2 times x, and I'm going to write this as 25 minus x squared to the 1/2. Differentiating both sides with respect to x, we will we'll have a product, and within that product we'll have a chain rule. So a prime of x will equal to, the derivative of the first is 2, and then times the second, and then plus the first times the derivative of the second. So we will have 1/2 times our something to the negative 1/2. Our something is 25 minus x squared, and differentiating the 25 minus x squared will get negative 2x. Good. All right, so simplifying, let's go ahead and let's see. Do you see that these 2's divide out? We can factor out another 2, and we can also factor out 25 minus x squared to the negative 1/2. And we'll be left with, on the first one, 25 minus x squared to the 1 power. And on the second one, we'll need a negative, and we'll have an x squared, and I think we're good to go on that. So continuing to simplify, we will have 2 times 25 minus x squared to the negative 1/2 times 25 minus 2x squared. So this gives us a prime of x is 2 times 25 minus 2x squared all over the square root of 25 minus x squared. Now, finding the zeros of this, we just need to set that numerator equal to 0. So that's going to give us that 0 is 25 minus 2x squared. So that'll give us that x squared is equal to 25 halves, which will give us that x is plus or minus 5 over root 2. Now we'll throw out that negative, because remember that we our base is going to be a measure, a distance, so we'll just keep the 5 over root 2, right? So that will be our C is 5 over root 2. Now, I don't know about you guys, but for the verification part, I certainly am not in the mood to differentiate this guy again. So I'm just going to run the first derivative test, which means we make our number line, and our x is going from 0 to what? Good, 0 to 5. And we have our critical number of 5 over root 2, which will be somewhere over here. And so we'll have 2 intervals, 0 to 5 over root 2, and then 5 over root 2 to 5. So if we test 1 and 4, I think that'll work out nicely. So a prime at 1 is 2 times 25 minus 2 times 1 squared all over the square root of 25 minus 1 squared, which will be positive over positive. So if you get the actual number, you'll get 2 times 23, I think we get 46, over root 24, which is greater than 0. So over here, we'll have a positive. And then a prime at 4 will be 2 times 25 minus 2 times 4 squared, all over the square root of 25 minus 4 squared. So that's going to give us a result in the numerator of, I think, negative 14 over root 9, which is less than 0. So this will be negative. So by the first derivative test, that means there's a relative max at x is 5 over root 2. So now we just need to find y. So remember that. So finding y, y was equal to the square root of 25 minus x squared. So y is the square root of 25 minus 5 over root 2 squared, which will give us y is, so we'll have 25 minus 25 halves, which actually gives us root 25 halves with a little algebra, which is 5 over root 2. Wow, what a surprise. So remember that the base was 2 times x, right? So here we would get, so the question they asked us was, what length and width should the rectangle have? So the rectangle should have a length of, so x will be the length, and remember x is 2 times 5 over root 2, so that would be 10 over root 2, and a width of 5 over root 2. Okay? Alrighty. So now we've got, I think it's our last problem. The U.S. Post Office will accept rectangular boxes only if the sum of the length and girth, which is twice the width plus twice the height, is at most 72 inches. So, what are the dimensions of the box of maximum volume the post office will accept? And we can assume that the width and the height are equal. So here we go. Let's make a picture of this. So we have a rectangular box, and the width and the height are equal. So we'll have something like if this is height and this is width, So we have our rectangular box. And so the sum of the length and the girth. So this here would be the length, all right? And the girth would be this measure. Okay, so that's the girth is that highlighted in blue. Right? So we've been told that the height and the width are the same. So we can make it all in terms of h. Okay, so far? Now, we've also been given that the girth is 2w plus 2h, and which we can say is equal to 2 times h plus 2 times h, since the width is the height, which gives us 4 h's. All right? And so now, let's figure out what the primary equation is. We want to find, I see the word maximum, we want to find the maximum volume, right? So here we go, maximum volume. Well, volume in terms of length, width, and height is the length times the width times the height, right? Now, we have some information here. So we know that W equals H, and we also know that the sum of the length and the girth, right, has to be at most 72 inches, right? So we said that the girth was 4h. So the length is L plus the girth was 4h, has to be at most 72 inches. So I'll just equal that to 72. So in isolating the length, we would get 72 minus 4 times h. All right, so the volume in terms of length times width times height was length times width times height. Now, the volume in terms of height alone is 72 minus 4h for the L, h for the W, and h for the h. So the volume in terms of height alone is 72h squared minus 4h cubed. Cubed. Good so far? All right. So we know that h has to be greater than 0, w has to be greater than 0, and the length has to be greater than 0. What else do we also know? Good. That 72 minus 4h, which is the length, has to be greater than 0. So 72 has to be greater than 4h. And that gives us 18 has to be greater than h. So that bounds h between 0 and 18. And remember, the width is the same as the height. So we've got everything bounded. Alrighty. Now, moving right along, let's go ahead and do our optimize. So to optimize, we find our critical numbers. So we had the volume in terms of h alone is 72h squared minus 4h cubed. So, first differentiating, the derivative with respect to h is going to be equal to v prime at h is 144h minus 12h squared. Finding the zeros, we'll have let's see, we can factor out a 12h and we get 12 minus h remaining. So 12h is 0, or 12 minus h is 0. We would get h is 0, or h is 12. So this one is not included in the domain, so our critical number C is 12 inches. So now when we go to verify, this is an easy second derivative, so I'm going to say use second derivative test. So we have v prime at h is 144h minus 12h squared. V prime double prime at h, so we're differentiating both sides with respect to h again. So we'll get v double prime at h is 144 minus 24h, and evaluating that at 12, we would get 144 minus 24 times 12, which is definitely less than 0. So h equal to 12 yields a relative maximum. All right, so now remember that to find other values, right, we need to find W and L. So W equals H, which was 12 inches, and the length was equal to, let's see, 72 minus 4H. So that would give us that the length is 72 minus 4 times 12. Oops, sorry, 72 minus 4 times 12, which will be equal to 72 minus 48. So the length would be 24 inches. So our conclusion is a box with a height of 12 inches a width of 12 inches, and a length of 24 inches yields the maximum volume. All right, so that wraps up optimization. All right, so the next section we'll cover from our Larson and Edwards Calculus text will be differentials. All right, so have a fabulous day. Bye.